Okay, the mic should be on now. Okay, the mic should be on now. Okay, the mic should be on now. Okay, I think we can start. Marcelo, can you double check that the audio is working? Okay. Okay, so we're going to start. So today's lecture, we're going to talk some more about doing parallel programming with OpenMP, and we saw a bit last lecture on Tuesday. We saw how we can essentially start threads and give the threads stuff to do, and have OpenMP distribute the workload in a loop over the different threads. And so that was quite convenient. We're going to look at somewhat more complicated cases today that are still very common and that you should know about. The thing that the previous cases of the last lecture all had in common is that everything that was done in each loop iteration was first of all the same and independent of the other loop iterations. So it was kind of natural that they could be done at the same time. So today we're going to look at a couple of cases where they're either not doing exactly the same in every iteration, or the different iterations depend on one another. And so the first kind of sort of loop dependencies that one can have are so-called reductions. So reductions are essentially when you have a bunch of data, a bunch of numbers, and you are going to reduce them down to, say, one number. Or you might have a matrix and you're reducing it to a vector. And so a typical example of that is if you take two vectors, x and y, and you take their dot product. Each of the vectors have, say, n elements, and so if two vectors of n, and we get one answer out. We do that by summing the product of each of the corresponding elements, so xy times yi, and then summing them all together. Now, the product themselves, xi and xy for each i, could be done independently. However, we will have to sum them all up into something, and that's where the dependency comes from. So these reductions have some sort of final dependency in them, one way or another. What we will do, and it's very typical for OpenMP, is start with a serial implementation and then try to add OpenMP. And when you're doing these kind of things, and I think we've gotten used to this now, we have our serial implementation, we save the output so that when we make changes to our code, we can test whether it's still giving the right answer. But the other thing that we will start doing now is also timing how long it takes, right? The whole point of doing parallel programming is to take something that isn't fast enough and make it faster so that we get our answer faster. If that's not the case, then there is no point. So here's a little code that does a dot product. The code on the right is in fact the dot product itself, but the code on the left is sort of the driver. Okay. So if the driver is on the left here, it sets up two arrays, x and y, and then fills them with elements, I. And then what we're going to do is we're going to take the dot product, so we're going to do xi times yi and sum them all up. That dot product is done in a separate function called n-dot here, so it takes two of these arrays. It figures out which one is the smallest size so that it doesn't go over the edge of one of the other, and sums all of them, all of the products together into a variable called tot. This function is called within the driver routine, the int main here, by just assigning n-dot and the result into dot, and it is wrapped in a tick and a tock. So The tick and the tock here are the timers, and it will actually just print out how long things took. We're also printing out the dot product, and because we know how it's filled, we can actually derive an exact answer and see if we get it right. So this is part of the OpenMP code that we hopefully git cloned last time. So if you do make serial underscore n dots, you will get this code compiled. The serial version is exactly what this is. We're running it. The dot product is 2.666 times 10 to the 21st. The exact answer is that's 2, so we've got the right answer. And this takes 0.1 second. It's pretty quick. Obviously, this is a toy problem. We wouldn't have to parallelize this in any sort of way, but we're going to do it anyway. Okay, so yes, we can parallelize the loop. And so one thing that we have to make sure is that we keep this tot variable up to date. And so our first try could be something like this. So this is the same n dot function, but in front of the for loop we do pragma OpenMP parallel that spawns the threads. So in our previous examples those were always 8 threads. So we will have 8 threads, and we do a for. That for here makes sure that the cases I to n-1 are divided over these over these 8 threads. And then we have to share x and y because we have to have access to that. Int I is defined inside of the parallel region, and so it's automatically private, which is what it should be. But then tot should also be shared because we want to add to the same variable tot so that we get the result out afterwards. So this will parallelize the loop. It will get these cases done at the same time by the number of threads that we assign it to. And so if we do that, and so this code is in OpenMP n.race. If we do that, then we see that the number of threads is 16. If we set the number of threads to 16, what we see is when we run it is the dot product is 2.64 something times 10 to the 20th. But that's not the right answer. The right answer was the same as before, 2.66 10 to the 21st. And it took 0.54 seconds. Remember, it took 0.1 seconds the slide before. So we can run it again, and we get another answer, which is also incorrect. So each time we run it, gets a different incorrect answer, and it runs slower than before. So wrong answer, and the answer varies. What went wrong here? This is horrible. It's slow and it's wrong. Why are we using OpenMP? Well, this is what's called a race condition, and here it's pretty clear, but it can often be very subtle and only appear intermittently. It means there's a bug, and these race conditions happen sometimes intermittently, so by sort of accident you get the right answer, except sometimes. And the bigger your problem is, the more likely you will get an issue like this. So for small runs you won't even see it. And it's a typical shared memory bug. It's a classical parallel bug, and it really comes down to the fact that we have multiple threads writing to the same variable tot. So you have a shared resource, in this case the variable tot, and multiple threads are writing to it. So it seems a bit strange that is an issue though, because if you look at the code, yes, they're all writing to tot, but as long as each of them does their addition, what is the problem? And so the problem is that when two threads are writing to the same spot at the same time, each of them doesn't wait for the other. They try to do this at the same time. And so we have to look at more detail at what actually happens when we update a variable like that. So suppose that we look at an even simpler case. We have one variable, tot, which starts off at 0, and then one thread wants to add 1, and the second thread wants to add 2, and those are the only two threads. We want to do it at the same time. The correct answer is 3, because we add 1 and 2. However, it's possible in a parallel code to see any of the answers 1, 2, 3 if we just let the threads update tot as they see fit. And the reason is that adding or updating a variable is actually not what's called an atomic operation. It's not just one operation and the order in which they are done is different. It's actually a composite operation. And it kind of looks like this. So we're going to follow thread 0 and thread 1 separately. Thread 0 will want to add the number 1 to tot, and thread 1 will add 2. And we'll see in time what happens. So in the first instance of time, what a thread has to do to start adding 1 to a variable is first to load the current value of that variable into one of its own registers. So the thread is running on a core. The core has a local memory that's called registers, and it loads it in there. So reads tot equals 0 into its registry. Then it can update its registry. So the registry gets added to 1, and then it stores the result in tot. But at the same time, just as it was updating its registry, is when thread 1 kicked in. And just by random chance, it kicked in 1 clock cycle later. And so it starts reading the variable tot into its registry just a little bit later. But tot is still 0, because tot lives in memory, not in the registers. And so it reads 0 into its registry. And then as thread 0 is storing its value back into tot, thread 1 is only updating. So it's updating its registry to 2. And then it stores its value, while thread 0 is already done, into tot. And so what we get is the result 2, because thread 1 was the last one to update it, and it didn't know yet about what thread 0 was up to. So it's wrong. And it's wrong because these are not atomic operations, and basically we're going to miss stuff. In fact, if you look at the answer, you see the answer for our n dot case is always less in the parallel case than in the serial case. Again, it's always wrong. And so that means we're missing parts. Now that is understandable perhaps, now that we know that it is composite, but it's not quite clear why this is also slower. We should get a wrong answer about faster because we're using multiple threads. And so the reason that it is also not faster is because this variable tot is living in a part of memory that is slower than registries. So if you imagine that you had a single thread that is trying to update and add to itself, it can keep that variable tot in its registry. But because we're sharing the variable tot, what the thread has to do to make that sharing true is to copy back its registry into the variable tot. And so this comes down to the fact that there is a memory hierarchy. This idea of a real shared memory system isn't entirely true. It's much more complicated than that. There is a shared memory, that's this red blob in the middle, that they all share. But then on top of that, there are other bits of memory that are either partially shared or not shared at all. And the reason that this happens is that memory is kind of slow. The main memory is slow, and so what people that build memory systems do is add pieces that are faster. Now you would maybe ask, why isn't all memory then made faster? This is expensive memory. So we have fast memory close to the core, but small parts of it, small amounts of it, and then typically, and that's called a cache. Each of the core has its own cache, and that cache is really fast, but it's really small. So what has to happen for this to appear to be a shared memory system is that whenever we need something from memory, it actually gets copied into the cache. This happens automatically. We don't do that programmatically. The memory subsystem does it for it, but it gets copied into the cache, and then from the cache we read it. And that wouldn't speed anything up if we only use our memory once, because we still have to read it, but it does speed things up if we reuse the data that is in memory. So in a serial code, when we're adding to one variable, we're reading tot once into the cache, and then we work in this fast cache. And then when we're done, we write it back to memory. Again, this happens automatically, but it does happen. What happens if we share tot among all of the cores is that each time they've updated tot, they have to write it back to memory. And not only do they have to write back to memory, somehow the memory system has to tell the other cores that this has now changed. And so there's communication going on, there's copying back to slow memory. This cache coherency that is done automatically is not free. So let's try fixing this. But let me just see if there's any Anything that I missed in the chat? Okay, so we're going to have to try and do this better next time in terms of audio and video, but you can try switching out the video, see if that helps. But I kind of doubt it. Okay, let's see. Okay, so we've got two things. We've got the fact that we have a wrong answer and the fact that we have a slow answer. So let's fix the wrong answer first. Let's fix the race condition, the fact that updates aren't atomic. So there's a couple of ways you can do this in OpenMP. The most general case where you have a bit of code or a certain number of actions that need to be done by the code that have to be done by one thread at a time, right? Because it's the fact that they update TOT at the same time that made this difficulty. So this is called a critical construct. The idea is that you say this particular region in the code is critical, and that means that it can only be done by one thread at the same time. It's fairly easy to put this in place. You look at the line of code that has to be done by one thread at a time only. So in this case, it's the updating of TOT, and you put pragma OMP critical in front of that. So every time that a thread hits basically this critical line, it waits for no other threads to pass this, to be busy with this. Only one thread does it at the same time. Okay, so let's see how that goes when we put that in. So we can compile this code. We can see if it gets the right answer, and it does. It gives the right answer. It's 2.66 like it should be. So we fixed the race condition. The only trouble is that now that we've put this critical in, it is 44 times slower than the serial version, which is horrible, right? This is not why we're trying to do parallel programming here. So the issue here is kind of clear. We have a parallel code, but for some reason the parallel version is 44 times slower than the serial version. Now, one way to try to fix this is to realize that critical is kind of heavy-handed. There's all kinds of locks that have to be done behind the scenes to make this work, and some operations like adding to a variable actually can be done without all of this extra software overhead by the CPU, turns out. And so to enable that, instead of doing critical, you can do atomic. And it kind of looks the same. You just have to say what kind of atomic you have. So atomic says this is critical, but use the instructions in the CPU to make this seem like an atomic operation. And so that should be faster because things that work in hardware tends to be faster than things that work in software. It looks very similar. You just add atomic, and in this case we're updating a variable, so we have to say atomic update. If you're just reading something atomically, it's atomic read. Write is if you're atomically writing without. So the plus equals is an update. If it was equals, it would be write. If it was a read, it would be read. And capture is a variation where you keep the old value, but that's a detail. So let's do that. Let's see what we get. We have our atomic updates. We run it with 16 cores. We get the right answer. Great. It is about twice as fast as the critical, but it's still not great. So the reason that it's still not great, that it's still slow, is that while it's now no longer like they're not updating at the same time and they're using hardware, we still have a shared variable TOT, and that shared variable means that every time that a thread updates it, it has to write it back to main memory, and the main memory is slow. To get around that, a common technique is to say, well, there's no reason to know the value of TOTs that each thread tries to access before we're all done. Each of the threads could update its own variable TOT, and then at the end we'll add all of those local copies. So each of so these are called local sums. Each of the threads will have a local sum. It will update its sum, and it can keep that sum in cache, and so it doesn't have to write it back. And then once all 8 threads are ready, they just basically copy those ones into the shared memory, so the main memory. So this is a way to implement that. So in this case, because we need to create these local copies, we have to separate out the creation of the threads and the work distribution by OMP4. So if our OMP parallel first, we enter this region. Once we've entered the region, we will create a local variable, a local tot for each of the threads. So there's 8. If OMP num thread was set to 8, there would be 8 threads entering here, and so 8 versions of local tot, but each thread just calls it local tot. And then a parallel for that only goes over a subset of regions, so it does the work distribution for us and updates local tot. So what will happen is local tot will be copied into cache. It will be kept in cache for the duration of this, because there's no reason to go back. It's not shared, it's private. And then once every thread is done, it will do an atomic update into the actual tot. So if everything happens exactly at the same time, then all threads do their portion of local tot and then try to do this at the same time. But because it's an atomic update, it's essentially serialized. But n is of the order of, I think, 1 million I had here. So we're doing 1 million less atomic updates or 1 million less writes into main memory. And so that should help a lot. So let's see. OpenMP num threads is equal to 16. We run this version of the code. It's called OMP n.local. And so we get the right answer. And finally, we get something that's faster. So this is 0.01715 seconds versus about 0.1 seconds that we had for the serial code. So it's 6 times faster, although we threw 16 threads at it. So it's not an ideal scaling. At least we're getting some bang for our buck now. Now, this idea of having local sums and reducing basically a set of numbers to a single sum is very common, and so it is actually implemented inside of OpenMP, and this is always called a reduction. And so OpenMP supports what are called reduction variables, and you kind of declare them the same way you do private and shared variables, but you have to say how those variables have to be combined. So let's just look at the code. But what it will do, what it can do, and it's something that we haven't done here, is every CPU will sum its own sum, but then if there's a lot of CPUs, a lot of threads, OpenMP can do more clever things than just summing them up atomically. It could actually say, well, let me sum up the values of 1 and 2 first, and 3 and 4 first, and then add those up and basically save some time summing up at the end as well, without you having to worry about how to implement that. So it kind of looks like this. Pragma OMP4, we're sharing x and y, and now the tot variable, rather than being shared, but there being a local tot variable, both of the things are happening if I declare the tot variable as a reduction variable. So that's what I've done here. And so reduction does essentially precisely what we saw in the local sum code. It creates private variables tot. Here they are. And so inside this loop, these are all private variables tot until it exits this parallel region, so the end of this code block, which is the for loop. When it exits that code block, it takes all of the private tot variables that there are and adds them up. That's essentially what this means. It reduces them to a single tot variable that corresponds to the externally shared variable called tot. So it does a lot for a tiny little clause here. And when we run that, we essentially get the same answer. We haven't gained in performance here. After all, we weren't doing that much parallelism. But the code is much simpler. And again, now the code is essentially the same code as the serial code with one extra directive. And as I said, that is sort of a common design feature of OpenMP. You try to make the code as close to the serial code as possible, and then add a pragma to make it parallel. Okay, so this is all we'll have to say about reductions. Excellent. Oh, okay, I see. Turning off the video helps a lot, so that's a good sign. Okay, we'll keep that in mind. Okay, so that's reductions. So that's where we have some dependencies, but they all go through a single variable that has to be added up at the end. The other thing that we haven't looked at, and that is quite common too, is the idea of having to load balance. So all of the iterations in each loop so far did the same thing, and each of those same things took the same amount of time. Let's look at it again. Every multiplication and addition is done the same for every iteration, and it will take roughly the same time for each iteration. There's no fluctuations in how long it takes, and that matters because what OpenMP4 does, it takes the n cases that we have and splits them up, in this case, in 8 big chunks. If the first chunk for some reason was done faster, that thread would not be used anymore and basically would be idle, whereas we could use it. So sometimes we have cases where that indeed happens, where we have load balancing. And usually when you have load balancing issues, the trouble is that each iteration that you do in your loop, you don't know how much time it's going to take. If you did, you could bunch things up by hand, but it's an unpredictability. And so OpenMP has some ways to do better work sharing than just plain dividing up the work in big chunks for each thread to do. So here's a sort of prototypical case of a very load imbalance calculation. This is called the Mandelbrot set. The Mandelbrot set is a boundary in the plane, in fact in the complex plane. And so what you have is the blue and the yellow region. There's a boundary between them, and there's a rule that says how to jump from one point in the plane to another point in the plane. Since this is a complex plane, it's actually just this rule, but that doesn't really matter too much for the principle of it. So every point is jumping in this plane, basically taking time steps, and some points keep inside this, keep bounded, so they stay bounded within the plane, and other points from the blue region escape. The trouble is, I don't know which one is which. The point is to determine which points escape to infinity and which points stay in a finite place. So we're going to make a map. We're going to divide this plane up in a grid, and for each grid point we want to know whether to color this yellow or blue. And we want to color it yellow if it stays inside the plane forever, and blue if it escapes. Now, that is a calculation we want to do, and once we have done the calculation, then we can make this picture. So we don't know this picture beforehand. This is the aim of the calculation, to get this picture. But the trouble here is, there's two troubles. First, we can never be sure that a point stay within the plane forever, because then we have to do the iteration infinitely many times. So we're going to put a cap on that. Say if in 1,000 iterations they're still within a radius of 2 from the origin, then we say, okay, they're staying in. But if they escape beyond 2 units from the origin, then we say, well, they've escaped. And in fact, you can show if they go beyond that, they will have in fact escaped. So we try 1,000 times, and if after 1,000 times they are beyond 2, we color it blue, and if not, we color it yellow. But of course, we will stop as soon as they have escaped. So some points will escape in, say, 1 step from here to outside, and we will color them blue after, say, 1 step. The yellow ones, we will have to take 1,000 steps to know that they are yellow. So there's points, the yellow points take about 1,000 times longer to compute or to determine that they are yellow than the blue ones. And that means that a simple grid is going to be very imbalanced. Just the code is also in the same OpenMP OMP Git repository that we had. It's called Mandelbrot and Mendel and Mendel Parallel. So the serial case here, I'm just going to point a few things out from the code. There's one routine that determines how many iterations it takes for a point to escape, or if it doesn't escape, it will return 1,000. or max, whatever the max iter is. So you give an initial point A, and then it figures out how many times it takes before it escapes. And then there's a function that uses that to make the map. So it creates a grid of n pix by n pix pixels within a rectangle of xmin by xmax by ymin by ymax. So those are the boundaries. And then there's some other stuff to display the map, because it's a graphical display application. That's not too important, but those are in there too. The important parts and the ones that take the most time are to make the map and to determine how many iterations there are. So if you want to run this, you can make Mendel and Mendel parallel, and we will see that the Mendel one takes 5 seconds to create this initial picture. By the way, if you do this with graphics, although I think by default the graphics has been switched off, you can select another region and you can zoom in and see this kind of nice fractal boundary and explore it. But we're just going to do the timing here. So the timing without displaying it is 5 seconds. We throw 16 threads at it, and the parallel version takes 1.3 seconds. And so that's faster, but definitely not 16 times faster. By the way, just to be more precise, here's the computationally most demanding function is to make the map. So we're creating a map here, my map from npix by npix, and this is the map actually just has stored the number of iterations, and then somewhere else in the code it gets translated into colors. So this is just basically a 2D array of the number of iterations it takes to escape. It goes over the x and the y, or the I and the j pixels, figures out what the actual physical x and y are rather than the indices, and creates a starting point A and figures out how many iterations it takes for A to escape, and puts that in the map. So there's 2 loops here. So we're going to probably do something OpenMPing there. But there's also a call to my how many iter, which is the actual heart of the calculation. So that kind of looks like this. How many iterations? So we have a starting point, and we iterate this map, b equals b times b plus a. That's a complex map that maps one point to another point, and then we check out whether it is a further away than 2 from the origin, and if it is, we stop. So the iteration is a sequential algorithm. So b gets transformed in every iteration, and so that means that there are strong dependencies here. I cannot really OpenMP this. I can't parallelize this because I need the previous version of b to compute the new version of b. So iteration I equals 1 depends on the result of I equals 0, and that goes on for all i's. So there is no possibility to parallelize this within this for loop because there's too many dependencies. You can tell OpenMP to do it, and it will do it for you, but you'll get the wrong answer again. So you don't want that. So what we're going to do is try to not parallelize this loop, because you can't. But the loops here, every iteration here, just depends on the values of I and j for that iteration. It doesn't depend on any of the other pixels. In other words, all pixels can be done simultaneously in principle, or at least in parallel. And so that's what we're going to do. So we're going to try and say, okay, here's a for loop. Let's parallelize this for loop, because this for loop, each I is independent. So we just put in a pragma OMP parallel for. We always want to do our default none so that we can be very specific on what is shared and what is not. And then we have to share my map, because we're building my map. The entries from the function, so xmin, ymin, xmax, ymax, the number of pixels, and the maximum number of iterations. And then that should go. So when we start this, when it hits this, it should get let's say 16 threads. It will divide the number of pixels in chunks of 16, and it will go. And that's exactly what we did for the Mendel parallel. So that's the one that we showed the example for. So I'm going to show the example with 8 threads, just because there's less drawing to be done. But imagine here's our Mandelbrot set that we want to compute. What happens when we do our OpenMP parallel 4 in this way is that it takes in the I direction, so let's say that's the horizontal direction, it splits it up for 8 threads into 8 chunks. So each thread basically gets a strip of cases to do. Now, we don't know which one is going to be more expensive than others, but once we have this picture, we can see that thread 0 spends most of its time calculating blue points, and blue points are quick. And same with 1. Most of the time it's doing blue points, and blue points are quick. So threads 0 and 1 and 6 and 7 were done very, very quickly. Whereas the threads that have a lot of yellow have a lot of points that take 1,000 times longer. And so basically what happens is that we run it with in this case 16 threads, but most of the threads after a little while are doing nothing. So we're actually not running with 16 threads full out. We're running with 16 threads for a little while, and then we're effectively probably running with like 4 threads, which is where a speed up is roughly 4 rather than roughly 16, which is what we should be able to get. So this is unfortunate because the load is unbalanced, but we didn't know this, so we could say, well, that's just the way it is. But it is a very inefficient way to use your threads, just to use your cores. You don't want this. And there's better ways. So we're going to try and do better in a number of ways, none of which can use knowledge of the answer, because the answer only comes out once we've done the computation. Okay, so by default, as I said, when you do OpenMP parallel OMP4, each thread gets a big chunk of the loop, right? One big chunk. That's nice. It's usually a good way to go, but here it's not. So what we can do instead of doing this default is we can schedule the iterations differently. So there's a clause that goes by schedule that we can add to the OMP pragmas to change the work sharing. And so we can do this in 2 ways. We can do this in a way that is static. That is to say, when we compile, it determines how it's chunked up, or dynamic, which means at runtime, depending on what happens and which threads are done, threads can be given more time. So that is a dynamic load balancing. The way it goes is either pragma OMP parallel for schedule static, and then there's an option that gives you the chunk size, so the number of iterations in each chunk, or dynamic, and again you can give the chunk size. So let's see what happens when we do static. So I think we have about 800 pixels wide, so for 8 threads that would have been 100 pixels for each. If we want to change that to 25 pixels for each chunk, we would have more chunks. So we end up with more chunks than threads. And that's good because the first 8 chunks are given statically to thread 0, thread 1, thread 2, and thread 7. But then the next chunks are given in the same way to the threads in order. That means that thread 0 initially got a chunk that was very lightweight, so it's done in no time, but then after it's done, it starts working on its next chunk, which is a much heavier chunk. So here it's actually contributing to the overall computation much more. So by having more chunks, although some of the threads will get chunks with less stuff to do, there'll be other chunks that they get that might be more heavy. So you just hope by chance that sort of balances out. And it does do better. So in this case, I took chunks of 25 with 16 threads. Now our speed up is 6.6. So that is better than we had it before. But we're still not quite satisfied. So the other way you can do this chunking is dynamically. And by dynamically, you have chunks. There's some default chunk size. I forgot what it was. Maybe it's like 16 or something. That it divides the iteration space into. But it works dynamically. So the first 8 are given to the 8 threads. But then whenever a thread is ready, it signals to the OpenMP runtime, hey, I'm ready, and it gets the next chunk, whatever is next in level. So this is more like a dynamic scheduling where you have chunks to do, you have resources, 8 threads in this case, or 16 threads in this case. Once a thread is done with its chunk, it gets a new chunk, not a predetermined chunk, but a whatever next chunk has to be done. So that is potentially much better, because you can't have the accidental case where a thread gets only lightweight tasks, because those lightweight tasks would be done quickly and it'll get another task that is not lightweight. So in this case, it doesn't really change too much, and that's because we were lucky the first time around, I guess. But another thing that does happen, because this has to be done dynamically, there is a scheduler busy that has to be told when a thread is not ready, that has to keep a list of the chunks, that has to give the next chunk to that. So there is a little bit of overhead to doing dynamic scheduling that costs some time. Now, at the end of the day, while just doing schedule static or schedule dynamic are good starting points, you're going to have to tune your code. You're going to have to figure out what is a proper chunk size that makes this optimal. And depending on the dimensions of your code, the compiler you're using, the architecture you're on, this changes. So there is a certain final set of tuning that you have to do. And the case that I was looking at, in fact, it turns out that the best chunk size was 1. So 1, because we're doing strips, still means 800 points in each. It's not entirely 1, but that's what we have. So the best case for static that I got was an 11 times speed up with 16 threads. That's not too horrible. And with dynamic, I got a little bit more speed up than that. And so that was the result. But this will vary. You'll have to change the chunk size. Remember, the chunk size is given by a comma and then another integer here to see what is the best. Now, that's great, but that's not all that there is to OpenMP. There's lots more, and we won't really discuss that here. There's ways to further divide this iteration space. So we're just dividing it in the x direction, basically. We can't divide in the y direction because parallel for only hooks up to the next for loop. But there's a way to make it basically consider multiple loops, and that's called collapsed. There's also ways where you can work with not so much loops or iterations, but with tasks. And so in our case, the tasks and the chunks were the same thing, but did the same thing. But you can imagine having an application where you have multiple tasks to do that aren't the same thing, right? Maybe one is writing to a file and another is doing some computation or something like that. And there might be dependencies between those tasks. You might have a for loop that calls a function that also has a for loop that can be parallelized, and so you might want to do nested OpenMP parallelism, where you have a number of threads for the outer loop and a number of threads for the inner loop. That is possible with OpenMP. You might want more fine-grained control than just having critical or pragma, where you basically say this region is critical, but only if you touch variable A or something like that. So you can use locks to deal with that. Those are also in OpenMP. So there there's things to use, or there's constructs to use parallelism that's in the chip. There are vector instructions in modern chips that can do single operations on multiple data, so SIMD, SIMD. You can have OpenMP express that this is what you want. You can work with thread affinity. Sometimes it matters if the thread is always on the same core or not, or on the same core as where your memory resides. Those are details that can matter for performance. And then what we're definitely not going to discuss here, because it would take way too long, is you can use OpenMP not just to parallelize over threads that live on your CPU. You can also do it to parallelize on a compute device like a graphics card, which doesn't share the memory, or doesn't necessarily share the memory with your code, but it's still in the same node. So if you're doing GPU programming, you can use OpenMP to do that, and basically do offloading of some of the computation to the GPU. That is a topic on its own that we can't really cover here. This was just about shared memory programming. Looks like we're doing okay. Okay, so I want to end with a couple of remarks about parallelism, because Marcelo talked a bit more generally about what it means to do parallel programming. Here we looked more at the details, like how do you do it, how do you spawn the threads, how do you divide the work. So I want to make a little bit of contact back with that sort of theoretical framework, and so and we're going to continue doing sort of technical stuff next week. So it might be important to sort of understand why we were doing this and what kind of things we were after. And so I want to make contact with this idea of the difference between